In this lecture, I'm going to be talking about another approach for an NER, name entity recognition, but we combine the idea of few-shot learning based on prototype learning with the idea of contrastive learning. So I'm going to be explaining this paper in 2023, Improving Self-Training for Cross-Lingual NER with Contrastive and Prototype Learning. In cross-lingual name entity recognition, self-training is commonly used to bridge the linguistic gap by training on pseudo-labeled target language data. However, due to suboptimal performance on target languages, the pseudo-labels are often noisy and limit the overall performance. So in this work, they aim to improve self-training for cross-lingual NER by combining representation learning and pseudo-label refinement in one coherent framework. Their proposed method, namely Conto-Proto, mainly comprises two components. The first one, they use the component of contrastive self-training to avoid collapse, for example. And the second one is prototype-based pseudo-labeling, because we don't have infinite amount of data. We need few samples of each class, so we are using few-shot learning. And the contrastive self-training facilitates span classification by separating clusters of different classes, and enhances cross-lingual transferability by producing closely aligned representations between the source and the target language. The cross-lingual NER aims to train a NER model with labeled data in a source language and evaluate it on test data in target language. So they formulate NER as a span prediction task. So given a sentence, we aim to extract every name entity and correctly classify it as entity type. Under zero-shot setting, labeled data is only available in the source language, and we leverage the unlabeled data of the target language during training. So firstly, the input sentence is fed through a pre-trained language model to obtain its last layer representation. Then we enumerate all possible spans, where to obtain the total set of spans, and then the representation of each span can be concatenation of the last hidden states of its start and end token. And the additionally introduces span length embedding, which is obtained by looking up the k-jth row of a learnable span length embedding matrix. So they obtain the final representation of sjk as just a concatenation of the jhk and, of course, the length embedding. Finally, the span representation is passed through a linear classifier to obtain its representation. So we are also learning this length embedding. After learning, we know that for each label, what is the embedding of that. So typically, self-training or teacher-student learning for cross-lingual NER first trains a teacher model on the available source language labeled dataset using this cross-entropy loss. Given an unlabeled target language sentence, the teacher model then assigns soft pseudo-labels to each span. The student model will be trained on the pseudo-labeled target language data as well, using a soft cross-entropy loss. The total objective for the student model in the vanilla self-training is the loss of source and the target. And the target, we've just defined it here. And the source is defined here. So the loss of source plus the loss of target is the total objective of the student model. So I have a playlist for contrastive learning, and I've explained a few papers about supervised contrastive learning, because contrastive learning is originally defined for unsupervised or self-supervised, let's say, for the application of computer vision. So this is the overall architecture of Cont Proto. As you see, we are using contrastive learning, we are using few-shot learning based on prototype-based pseudo-labeling, and of course, it's not just token by token NER, but it is span-based NER, which is a recent idea for NER based on span prediction, because we may have nested NER, name entities. And the supervised contrastive loss is just the log of this fraction. And supervised contrastive learning helps to pull source language entities of the same class together while pushing clusters of different classes apart, which introduces a clustering effect and thereby benefit classification. For pseudo-positive pairs, as we mentioned, it does not explicitly optimize target language representations or promote cross-lingual alignment. Therefore, we propose to construct pseudo-positive pairs which take target language spans into account as well. So we expand the multi-viewed span set by adding in unlabeled target language spans, and M here is the total number of spans from the source and target language sentences. And for source language spans, Y sub I is still its global label. As gold annotations are not available for target language spans, we instead treat the model's prediction at the current training step as an approximation for its label, Y sub I. So if it is in the source, we consider it as gold, but if it is in the target, then we take the argmax of p theta. So likewise, we construct positive pairs from entities with the same label. As an example, positive pairs for the person class might be composed of two source language names, one source language per name and one target language, and so two target language spans predicted as PR. So we also include a consistency regularization term to further enhance the model's robustness. So this is the KL. We want to minimize KL divergence between p theta and p prime theta. So each span Si yields two probability distributions because each sentence is passed twice through the NER, and each span yields the two probability distribution. So this is a way that we are using regularization. So this is the final term. So we use contrastive learning, and we take the source and the target, and finally regularization. So to start off, we first define a series of prototypes, and each corresponding to a class C. So this is a prototype for class C, and a prototype is a representation vector that can be deemed as the cluster centroid of class C. So we have different prototypes. Naively, phi sub c can be calculated by just averaging, just like the original paper. However, this means the prototype will remain static during the next full epoch. And this is not ideal, as distributions of span, representations, and clusters are vigorously changing, especially in the earlier epochs. And hence we adopt a moving average style of calculating prototypes. So it's like a moving average way of calculating the prototype. We mean that we iterate through a batch of mixed source and target language spans and update phi sub c as the moving average embedding for spans with label c, because only the label c is important. And then we do pseudo label refinement. So typically, prototype learning classifies an unlabeled sample by finding the closest prototype and assigning the corresponding label. However, this may cause two problems. Assigning a hard-won labels forfeits the advantages of using soft labels in self-training, and as the closest prototype might differ between the consecutive epochs, there's too much perturbation in pseudo labels that makes training unstable. So we again take a moving average approach to incrementally update pseudo labels at each training step. So given a target language span at each epoch, its soft pseudo label from previous epoch is updated like this. And of course, margin-based criterion, we use NER is highly class imbalance task, where the majority of spans are non-entity. As a result, non-entity span representations are widespread, and as later shown, the O cluster will be significantly larger than entity types. Therefore, a non-entity span at the edge of O cluster might actually be closer to an entity cluster. Consequently, the above prototype-based pseudo-labeling will wrongly shift its pseudo-label towards the entity class and eventually result in a false positive instance. So to address this issue, they further add a margin-based criterion to enhance prototype learning. Intuitively, a true entity span should lie in the immediate vicinity of a certain prototype. Thus, we do not update pseudo-labels towards entity classes if the span is not close enough to any of the entity prototypes. The similarity between the prototype and any span representation does not exceed a margin R. So we care about the margin to be as robust as possible to exclude noise. So as non-entity spans are widely distributed, we do not apply extra criteria and update spans as O, as long as its closest prototype is phi of O. So we notice that different entity classes of different target language might have varying cluster tightness. And thus it is not judicious to manually set a fixed margin universally. Instead, we automatically set class-specific margin R sub C from last epoch's statistics. So by calculating the average similarity between the target language spans predicted as class C and prototype phi of C, you can calculate R sub C. This is the class-specific margin. And by using TSNE algorithm, which we use for visualization, we can see different spans. And this is the vanilla self-training that everybody can do, but this is the model proposed in this paper. As you see, it has a better separation, better classification of name entities. But still, you see, O is huge. O is huge, and we have tiny areas for location, person, and those things. And of course, like any other algorithm, it has its own limitations.